These are 7 ancient sites where the physical evidence left behind does not match the tools we know existed, and the gap between what was built and what should have been buildable is so consistent across so many cultures and centuries that it demands a serious forensic look. This isn't about structures that are merely impressive, it's about sites where engineers, material scientists, and precision machinists have examined the evidence and concluded that something doesn't add up. The tolerances are too tight, the weights too extreme, the material hardness too high for the tools on record. What follows is a forensic audit of 7 sites: what was built, what tools existed, and what the distance between those two things actually means. Let's start in India. Carved directly into a granite hillside in the state of Bihar, 4 rock-cut chambers were commissioned by the Emperor Ashoka during the Maurya period and given to the Ajiticus sect, an ascetic religious movement that no longer exists. Among the oldest surviving rock-cut chambers in India, the caves have drawn attention from engineers for over a century, and the reason has nothing to do with their age. The interiors of the Lomas, Rishi, and Sadama caves are polished to a mirror, finish the kind that produces a clear reflection on granite. Granite sits at 7 on the Mohs hardness scale due to its quartz content, and achieving a mirror-grade polish on it today requires a multi-stage abrasive process: coarse grinding, medium, lapping, fine lapping, and then polishing compounds run at 3,000 to 8,000 grit, all done with electric rotary tools and controlled pressure. The Sadama cave interior runs approximately 10 meters long and nearly 6 meters wide, and that polish covers the walls, the ceiling, and the floor uniformly. No polishing tools have ever been recovered from the site. Conventional archaeology points to quartzite, rubbing stones, and fine sand abrasives applied by hand over extended time, and that method is technically possible, but replicating this result at this scale on a vertical ceiling with no mechanical assist is a different proposition entirely. The caves also carry a striking acoustic property, a powerful resonant echo that fills the polished interior, and whether that was by design or coincidence is still an open question. E.M. Forster based the Barabar Caves in a passage to India on this place, writing in 1924 that they were ancient, inscrutable, and impossible to fully explain. And the engineering problem he didn't know to describe has only grown more specific since. Most people know Baalbek through its Roman temples. The Temple of Jupiter, the Temple of Bacchus, and Roman engineering at its peak is genuinely extraordinary. The part that stops modern engineers cold sits underneath all of that in the foundation platform that the Romans built on top of. Set into the western wall of that platform, the 3 stones, collectively known as the trilithon, each weigh somewhere between 800 and 1,000 metric tons, positioned at roughly 8 meters above ground level, fitted tightly against adjacent stone with minimal mortar. Moving stones of that size at ground level would already qualify as one of the most demanding logistics operations in human history. And these were placed elevated into a structure. The trilithon isn't even the largest stone at Baalbek. About 900 meters away, still lying in its quarry, is the western stone, Haja al-Hila in Arabic, measuring approximately 21.5 meters long, nearly 5 meters wide, and over 4 meters high, with an estimated weight of 1,650 metric tons. German Archaeological Institute excavations in 2014 identified a 3rd quarry stone, estimated at roughly the same weight, making it potentially the largest worked stone block ever identified. Here's where the modern engineering comparison lands the lie. Here, LR 13,000 is the largest conventional crawler crane on Earth, with a maximum lifting capacity of 3,000 metric tons under optimal conditions, full counterweight, prepared flat ground, no extended radius at 30 meters of operational radius, which any real placement would require. That capacity drops to somewhere between 700 and 900 metric tons, and the machine itself requires a prepared load-bearing surface that simply didn't exist at ancient Baalbek. Moving the western stone by modern means would require multiple synchronized cranes, a custom hydraulic skidding platform, or purpose-built ground infrastructure. No single piece of equipment can do it alone. Roman engineers were brilliant, their methods well documented, and the temples above are proof of what they could accomplish. The pre-Roman platform they chose to build on, who constructed it, and when and how, has never been formally resolved. Beneath the necropolis at Saqqara, a system of tunnels and chambers cut into bedrock served as the burial place for the Apis bulls, sacred animals associated with the god Tar, interred here from the New Kingdom period through the Ptolemaic era. Set into alcoves, along these tunnels are 24 granite sarcophagus boxes, each approximately 3.7 meters long, 2.3 meters wide, and 2.3 meters tall, with the box and lid combined weighing an estimated 70 to 100 metric tons. All 24 are cut from a swan rose granite, rated 6 to 7 on the Mohs scale. The anomaly lives in the interior surfaces. Engineer Christopher Dunn, author of Lost Technologies of Ancient Egypt, measured the interior walls of multiple boxes using precision straight edges and dial gauges, the same instruments used in industrial manufacturing quality control, and his published findings put the interior surfaces flat to within 0.002 inches, or 0.05 millimeters, a tolerance consistent with precision machined industrial surfaces. The sourcing here deserves directness. These measurements come from Dunn's own published work, not an independent peer-reviewed study, and that caveat carries weight. His methodology is documented, his engineering credentials legitimate, but the 0.002-inch figure hasn't been formally replicated in academic literature. What's harder to set aside is the scale of the question. CNC surface grinding of granite typically achieves flatness to plus or minus 0.1 to 0.3 millimeters. Reaching 0.05 millimeters requires lapping grade finishing done by hand across roughly 8 to 9 square meters of interior wall underground with no electric light. And there are 24 of these boxes, each one presenting the same question at the same tolerances, cut from some of the hardest stone available to Egyptian builders. Coricancha was the most sacred temple complex in the Inca Empire, the golden enclosure dedicated to Inti, the sun god, built in Cusco and expanded by the Emperor Pachacuti in the 15th century. When the Spanish arrived in 1533, they built the Church of Santo Domingo directly on top of it, and after major earthquakes hit Cusco, the Inca foundation stood while the Spanish construction above them did not. A structural outcome worth keeping in mind, the joining method used across Sacsayhuamán, Tiwanaku, Ollantaytambo, and Pumapuku is one of the most technically demanding details in ancient construction anywhere in the Americas. T-shaped or I-hap channels were cut into the tops of adjacent stone blocks, and molten metal was poured directly into those channels in the field, cooling in place to form a metal staple that locked the blocks together. Metallurgical analysis, including work published in Latin American antiquity, confirmed these clamps as copper alloy bronze. Bronze melts at somewhere between 950 and 1050 degrees Celsius, depending on tin content, and pure copper reaches its melting point at 1085 degrees Celsius, nearly 2000 degrees Fahrenheit. Sustaining that temperature requires a furnace. Keeping the molten metal fluid during transport to the pour site requires a crucible rated for that heat, and the pour itself has to complete before the metal cools, which gives workers a window of seconds to minutes at most. Cusco sits at roughly 3,400 meters above sea level, and Tiwanaku at nearly 3,840 meters, where lower oxygen partial pressure makes sustained high-temperature combustion harder to achieve and harder to maintain. Physical evidence of in-situ pouring metal flash and overflow, still visible on some stones at Tiwanaku, rules out the simpler possibility that the clamps were cast elsewhere and pressed cold into the channels. no portable furnace or casting apparatus has been recovered from any of these sites. Excavations beneath the step pyramid of Djoser at Saqqara turned up approximately 35,000 stone vessels, not pottery, but stone cut from granite, basalt, schist, and diorite. Diorite rates 6.5 to 7 on the Mohs hardness scale, and copper, the primary metal available to pre-dynastic Egyptian craftsmen, rates approximately 3. Early bronze gets you to about 3.5. The material being cut was roughly twice as hard as the tools cutting it. Among these vessels, the diorite examples present the sharpest engineering problem. Some carry walls as thin as 2 to 3 millimeters, with narrow necks and interiors that are wider than the opening, meaning the cavity was undercut. Larger inside than the neck allows any direct rigid tool to access. Egyptologist Dennis Stocks conducted experimental archaeology documented in Experiments in Egyptian Archaeology in 2003, demonstrating that copper tube drills with quartz sand abrasive slurry can achieve material removal in granite and diorite, which addresses the cylindrical board interior. The narrow neck undercutting problem remains a separate question, one where the geometry itself prevents direct access tooling from reaching the widest interior point through a smaller opening. Then there's the quantity. 35,000 vessels, many in hard stone, with consistent thin walls and finished interiors, produced by a civilization working in copper and stone. And whatever technique accomplished this, it accomplished it at a scale that looks by any reasonable measure like organized industrial production. Just above Cusco sits a 3-tiered ceremonial complex built primarily under Pachacuti and his successors in the 15th century, with walls composed of limestone and andesite blocks estimated at between 125 and 200 metric tons each. The weight is not the primary anomaly here, the joinery is. Rather than stacking in simple horizontal courses, these stones interlock in 3 dimensions. 4. Each block individually shaped with multiple faces, each face contoured to match its specific neighbors, and no 2 stones sharing the same form. Some blocks make contact on 5 or 6 faces at once, and the famous 12-angle stone, found in an Inca wall in Cusco, demonstrates 12 perfectly fitted contact faces on a single block, each one seating precisely against a different neighbor. No mortar was used anywhere in the construction. The fit between the stones is the joining mechanism, and that fit has held through major seismic events that destroyed Spanish colonial buildings constructed nearby using conventional mortar. Cusco sits in a high seismic zone, and modern structural engineering assessments confirm the Inca interlocking system performs better in that environment than Roman-style mortared construction would. Fitting a multi-hundred-ton stone against multiple existing neighbors on up to 6 faces simultaneously requires precise measurement of all contact surfaces in 3 dimensions, transfer of those measurements to the new stone before cutting begins, and some method of test fitting, which for a 200-ton block is not a casual or reversible operation. The Inca toolkit on record includes stone hammers, bronze chisels, and measuring cords with no documented 3D measurement instruments, no scribing templates, and nothing that obviously bridges the gap between those tools and the result. How a complex 3-dimensional geometry transfers from an existing stone face to a new block accurately enough that 6 faces seat simultaneously when 200 tons descends into position has never been formally explained in a way that accounts for what's actually standing at Sacsayhuamán. An obelisk abandoned mid-excavation in a granite quarry in Aswan, Upper Egypt, has sat in place for over 3,000 years, and because it never moved, it preserved something completed obelisks cannot: a record of its own production. Had it been finished, it would have stood approximately 41.75 meters tall and weighed around 1,168 metric tons, making it the largest obelisk ever attempted. A crack discovered during quarrying ended the project before extraction. The standard explanation for Egyptian obelisk quarrying rests on well-documented evidence.
Workers used dolerite pounding balls, hard igneous spheres weighing between 5 and 12 kilograms, to pound channels around the obelisk by percussive force, and dolerite is hard enough to work granite effectively. The channels surrounding the unfinished obelisk, roughly 60 to 75 centimeters wide on 3 sides, are consistent with this method, and experimental archaeology supports it. The surface evidence is where things get complicated. Alongside the expected percussion marks, the sides and base channels of the obelisk carry elongated, curved, concave grooves with smooth walls, and those marks don't match what dolerite pounding produces. Percussive impact with a hard ball leaves a rough, crated, irregular surface, scattered circular impact points, and the grooves at Aswan are instead elongated and smooth-walled, more consistent with a rotary or dragging motion than with direct percussion. Researchers outside the academic mainstream have documented and filmed these marks extensively, and that distinction matters.
Unlike the dole-width pounding evidence, this specific groove morphology hasn't been formally addressed in peer-reviewed Egyptology. The standard explanation hasn't been tested against these particular marks in academic literature, which means the unfinished obelisk, uniquely positioned to tell us exactly how Egyptian obelisks were made, contains details that the official account still doesn't fully cover. 7 sites, 4 continents, multiple centuries and civilizations with no documented contact between them. At Barabar, mirror-finished granite covers large interior surfaces, and no polishing tools were left behind. At Baalbek, individual stones exceed the usable lifting capacity of the world's largest modern crane, and the stones already in the platform were elevated 8 meters into a structure. In the Serapeum tunnels at Saqqara, 24 granite boxes, each weighing up to 100 metric tons, carry interior surfaces measured to precision machine tolerances by a qualified engineer. At Coricancha, bronze was poured at over 1,000 degrees Celsius directly into stone channels in the field at altitude, with no trace of the equipment required to do it. In pre-dynastic Egypt, 35,000 stone vessels were produced in materials harder than the available tools, including thin-walled, undercut interiors in diorite that direct-access tooling cannot physically reach. At Sacsayhuamán, stones of up to 200 metric tons were fitted simultaneously on up to 6 faces, with no mortar and no documented measurement technology to explain how the geometry transferred. And on the unfinished obelisk at Aswan, groove marks inconsistent with the tool officially credited for making them have gone unaddressed in academic literature. Any one of these sites taken alone could be argued as the product of time, patience, and human ingenuity pushed to its upper limit, and that may well be the right answer. The conventional explanations for most of these sites aren't impossible. They're strained. What's harder to set aside is the pattern, the same gap appearing across unconnected cultures, the same distance between the tools on record and the results left in stone on every continent where monumental construction took place. That gap has a name, the mechanical delta, and it refers to the space between what primitive tools should produce and what actually exists. The gap is real, it's measurable, and it remains unexplained.